welcome back to the channel. I'm going to talk to you about what I've been seeing so far as I've gone around the house looking at a lot of different materials with a portable near-infrared spectrometer. And this is a device that's great for looking at various forms of carbon bonds, so carbon-carbon, hydrogen, ideal for polymers, plastics, even waste and soil materials. And so I've looked at couches, the floor, different soils, textiles, for over-the-counter pharmaceuticals. And as I'm working through this data, I found something that kind of jumped out to me. And so I will eventually go through the full data processing, but I want to tell a small story about one of my samples. So here in this table, you can see I've got 89 samples, toilet tissue, facial tissue, various textiles and upholsteries, various over-the-counter pharmaceuticals and herbal supplements. And one of the areas that I was particularly interested in were the soil materials. And in particular, some that were from the dryer, Lint, so that trap that collects all the loose fabric pieces, and the vacuum. And we have a vacuum on the main level, which is primarily hardwood, so it's getting food that spills off the table, and our large area rug, and our upper, which is all carpeted. And so as I was looking at the data to do the larger analysis, something kind of jumped out to me. Let me show you. So here is our notebook where I'm doing the data processing. I've got several libraries that are typical for signal processing, data visualization, and some unsupervised analyses. My typical signal processing functions apply standard normal variate and apply sophisticated, as well as the metadata that I just showed you. So this is the data that helps us to understand what those chemical signals are, the metadata. And then I have a host of instrument data that I've downloaded as a CSV from the wavelength range of 1450 nanometers to 2450 nanometers. And what I'm going to do next is merge that data, merge the metadata with the analytical data, and then average based on the sample ID. So there are several replicates within each of those measurements where I have upwards of about 500 different measurements that we're going to average and reduce down, in this case, to 89. There will be other cases where we will decide how we want to handle aggregating that data, but in this case, we're just going to take the average. So one thing that's particularly interesting was what I discovered when I began applying my manifold learning technique. So this is an unsupervised technique that helps us to understand the data by reducing its dimensionality. And in this case, I'm only outputting two different components with the perplexity of 15. And this parameter here allows us to determine how it looks for its neighbors, how far to look, what type of relationships to prioritize as it begins then transforming that data into this lower dimensional space. Next, I will convert this into what I'm just going to call a scores data frame, analogous to what we would use for PCA, and then label the columns as TSNE1 and TSNE2 for my two components. And then I will re-index that with the index values from the main data frame, and then concatenate that back to the metadata so that we can leverage all of the understanding we have about the material IDs and other properties. So let me run these cells. And what we have here, again, is the analytical data tied to the metadata. And now the model parameters and output, TSNE1 and 2, with that same metadata. So plastic container, the general material type, specific material. And again, I will have a larger video where I go over more of this. I'm just focusing on one particular component. And so next we're going to use Plotly Express, the scatter plot method, to visualize this data. So this TSNE 1 and 2, and with an opacity of 0.9, and we're going to color by material type. So whether it's a plastic container or other form, with lots of other data that we can use as the hover data. And I'm just going to call this all data scores plot. And so when we look at this data looks quite complex, but we can already see that there are some groups that are forming. And initially, these clusters might look somewhat random, but we will begin digging through this as we evaluate which data should we include, how do we subset the data to make more sense. But these are all the types of materials that are found around our home, and in this case, my home, again, ranging from a rubber balloon to a plastic bag, various textiles and pharmaceuticals, facial tissue. So if there's anything else you think I should look at, let me know. I am happy to go around and continue the testing. As well, I will try to figure out what type of outdoor samples make sense to include, maybe the soil, the physical soil around the home, some of the flowers that if I dry them out, maybe I can get rid of some of that water peak that I've seen in previous testing. But in any case, I want to focus on this soil here. So let me change how I plot this data, where instead of coloring by type, we color by where type equals soil. And like this greatly simplifies what this data looks like. We can see that we have 2 measurements, 2 soil samples here, and 2 samples labeled soil here. And it's really interesting because when we look at what these 2 soil samples are near, we see based on the specific material that it is cotton and polyester. We see that this is more cotton. And these are the soil samples that were the lint from the dryer. So we can see that as these materials go in the dryer and those particles are removed from the fabrics and collected on the trap, and we look at this, the actual chemical composition is very similar to that of the cottons and other clothing that were included in this study. On the other hand, when we look at these 2 soil samples, these are from the vacuum cleaners that we have around the house, and they're actually near other materials like these polyethylene samples and many other plastics and synthetics that are consistent with the composition of the 4 and maybe some of the other spills that this picks up. And as it's homogenized in the vacuum, we're capturing that signal and that variability within these samples. And I will continue to collect these soil samples because I'm sure they might tell us something over time. But in any case, you can see the value of robust chemical testing, as well as the ability to reduce down the dimensions and start exploring the patterns within this complex data. If you want to see more, like, comment, subscribe, and I'll see you in the next one. Peace.